So we want to look at a little bit more closely at optimization, because what we did in our first lesson on optimization really was just more looking at how the derivative can be applied to rates of change in other contexts than just motion. Okay? But here, the idea of optimization, all right, we didn't really get to talk about all that much in the previous lesson, okay? So what is optimization? Optimization is really, you could say, finding the, and I'll put it in quotation marks, the best solution. Okay? Now I put best in quotation marks because best might change depending on the situation. Okay? If I'm talking about money, you might automatically think, oh, more was going to be the best, all right? So I'm looking for maximum. Well, not if we're looking at a function that has to do with costs, all right? I want to minimize my costs, so in that case, the minimum would be a best solution, okay? Or there might be, an area problem where we have to use a certain amount of perimeter and we want to enclose the maximum area. Okay, well there, obviously the best solution is the one that gives us the area that is at its maximum. Okay, now as I'm talking about maximum and minimum values, you're automatically thinking of what? Derivatives. And how do you find max and min values with the derivative? A sign diagram. Set it equal to 0. Okay. So this kind of step-by-step process I thought was helpful, especially those of you who kind of like having more of a analytical, you like having a game plan a little bit more concrete in your head when you approach problems. But let's just look through this, and then we'll do a couple of problems here to work our way through, okay? Step 1, if it's a situation that lends itself to having some kind of a diagram, then draw a nice clear diagram that shows all of the given information, okay? Make sure you show the information. That really will help avoid a lot of confusion, okay? If you can really identify not just kind of what you're given, but really specifically in relation to a formula or in relation to, variables in the formula, exactly what you're given, that's really going to help, okay? Now, step 2 is to construct a formula. Sometimes you'll be given the function that you're supposed to use. Okay, in our first example, we're given the function. Other times, you actually have to construct the formula. Now, how do you do that? Okay, well, in the problem, it's going to tell you to find the maximum whatever or the minimum whatever. That whatever is what your function ought to represent. Okay? And that's what this says when it says the variable to be optimized as the subject. Okay? All right. So if your problem is asking you to find the minimum costs for X number of things, then your function you're going to write as C of X to represent cost. If you're asked to maximize your profits, then you would probably want to come up with some function P of X for profit. Okay? So whatever you're trying to maximize or minimize, whatever you're trying to optimize, is what you want your variable to represent. Okay? Now, initially, you may use a formula that has multiple variables in it, okay? But, as it says here, it should be written in terms of one convenient variable, all right? So if you're dealing with area and it uses length and width, that's a good starting point, but then you need to look at the other information you're given and determine, okay, so how could I express the length in terms of the width or the width in terms of the length so that I only have one variable in here, okay? And then also, this is a really important one. Write down what domain restrictions are there, okay? What domain restrictions are there on X? Sometimes these are given to you. Sometimes you need to think about this logically. Can our answers only be integers? Okay? In that case, you may find a critical value that's at like 8.1. So guess what? You should probably try 8 and 9 to see if your max or min is there. Okay? And you're not finding necessarily the max or min of the function itself, but you're finding the max or min of the function within the realistic solutions. Okay? So there's a lot that can go into these, but you just got to think through it. Okay? So then step 3, you've got your function, take the derivative. Okay? And then find where it equals 0. All right? So that's the easiest part, the part that we've been doing a ton of, okay? And then step 4. Step 4 is where we're really finding our solution, okay? Now it says if we have a restricted domain, the maximum or minimum may occur either when the derivative is 0, at an endpoint, or at a point where the derivative is not defined, okay? So, derivative is 0, derivative is not defined. Remember, those are the critical values, okay? But also, look for those endpoints, okay? Look for those endpoints. And again, I illustrated this a little bit the other day, but this is the idea that, okay, if we've got some function here, and it looks like this, and we figure out that the domain is that it has to be between here and here, okay, then if we're finding the minimum value, yeah, that's at a local min, okay? But if we were trying to find a maximum value, it's not going to be at the local max. It's actually going to be over here at this endpoint. Okay? That's not something that you're going to get from the calculus. That's something that you would have to get from using logic and thinking about the situation. Okay? So, do make sure that you consider your domain and check the endpoints. And then finally, step 5, I don't require that you write your answer in a complete sentence, but we do want to make sure that you specifically answer the question. All right? Please don't do all the hard work and then not actually answer the question. All right? So, this is a nice framework. It's a pretty good problem-solving strategy for these. So let's actually look at a few examples, okay? And I've actually gone through the five steps here to help us do this one. It says a 4-liter container must have a square base, vertical sides, and an open top. Okay? Find the most economical shape which minimizes the surface area of material needed. Okay? Well, first of all, I'm thinking through this, all right, and before I even start trying to solve anything, let's draw a picture. Okay? So I know the container has to have a square base, all right? So let's make a square base. And the fact that they said it's square is significant. So what has to be true? Yeah, the sides all have to be the same. So I may change this later, but let's go ahead and make the sides of my square base each x. Okay? Now, it says it has vertical sides, so the sides are going to go straight up, straight up, straight up, and straight up. And it also has an open top, which means there's no lid on this container. It's just open. So, and that's important because I don't need to cover the top. All right, so none of my surface area is going to, that's not going to be included in my surface area. Okay? Now, what else do I know about this? Okay, well, I don't know the height. All right, I don't know the height, so I'll put that down. But I do know this is 4 liters. Now, 4 liters, that's a unit of what? Volume. It's a unit of volume. Okay? So the volume is 4 liters. Now, I put on here a note. This is something you kind of have to be careful about. A note that 1 liter is 1,000 milliliters, and 1 milliliter is 1 cubic centimeter. Okay? That's actually how, well, if you're in the hospital and you hear them talking about cc's, those are cubic centimeters or milliliters, okay? Or if you read a medicine bottle and it says sometimes it'll take this many cc's or this many milliliters of medicine, especially with like kids' medicine and stuff, okay? So this volume is actually 4,000 cubic centimeters, so centimeters cubed.
Do you have to memorize it? Like
the 1 milliliter is a cubic centimeter?
Yeah.
You know, on the IB exams, they really don't do much with unit conversions. I mean, maybe not like that necessarily. Like they may say kilometers and then you have to deal with meters or something like that. That's simpler. They don't really, at least not that I've seen, throw these kinds of curveballs at you necessarily. Okay, so let's think about, we've got a picture, we have our given information written down there. Let's go ahead and see if we can come up with a formula for the variable. Okay, now what are we trying to optimize? Minimum surface area, okay? So let's make surface area, we'll use S, or you could use whatever you want, A. But how do we find the surface area of this box up here?
X squared plus x squared.
Wait, what did you say?
X squared.
There is an x squared. Let's think in concept actually before we even get any variables in here. Surface area is the area of all the sides, right? Okay, all the surfaces. So you have the area of the bottom plus the 4 sides.
So it's x squared plus 4x.
Okay, so yeah, it's x squared plus each side is x times h, and there's 4 of them. Okay? So now we almost have our function that we need. The problem is we have 2 variables in it. So since there's a couple of x's and only one h, let's try to write h in terms of x. All right, what would we use to do that? H equals x? It might if this were a cube. And who knows, we might find that that is the best solution. I don't know. What other information are we given?
Um, it's 4 liters.
It's 4 liters, okay, so there's volume. How do we calculate volume of a box?
X
Times width times height.
Yeah, okay. So we could say 4,000 is length times width times height, x squared h. Okay. So now I have something where I can express h in terms of x. H is 4,000 over x squared. See how this works? Okay. Start simple. Just think in concept. What formula do I need? I need the area of the bottom plus the 4 sides. Alright, well how do I get those? And then if I have more than one variable, alright, what other information am I given? How can I use that here? Okay, so now S is x squared plus 4x times 4,000 over x squared. And that, of course, we can simplify so that we have x squared plus 16,000, and you could say over x, or you could say x to the negative 1 power, since we're going to differentiate. Because you have an x on the top and an x squared on the bottom, so it'd be over x. Over x or x to negative 1, either one. And look, now we actually have a function of x. Okay? Before we could only say s, because we had multiple variables in there. Now we can say s of x equals this function. Okay? What limitations are there on the domain? What could x equal?
Anything above 0.
Okay, x has got to be greater than 0. Or else you don't have a rectangle, or you don't have a square base. Okay. Is there any maximum?
4,000.
And why do you say that?
If x is 1. I don't know.
The smallest x can be a 0. The smallest h could be is 0. All right. Now,
It can't be.
Wait, what?
well, hang on. It can't equal 0. So x is going to have to be
X can be.
smaller than the square root of 4,000, right? Because if I had the square root of 4,000, h would be 1.
No, because if you had x, let's say x is 4,000, you can just make h some fraction.
Okay.
So x can go to infinity,
So theoretically, x can go to infinity?
and then h does the exact same thing. 0 to infinity.
Okay. Yeah, that makes sense. Now, if we were adding x with h, there would be a maximum. But yeah, since these are multiplied together, you're right. H could theoretically get infinitely short, and we just have an enormously big square, all right, with a super tiny height. Okay, so theoretically, in the domain in this case is just x is greater than 0. So, are we going to need to find any kind of endpoints? No, because there really aren't any endpoints here. Okay? So let's go ahead and let's find the first derivative and the critical values at this point, okay? So s prime of x is going to equal what?
2x. Minus 16,000 next to the -2.
All right, yeah. 2x minus 16,000 x to the -2. Now, if we set that equal to 0, how you choose to solve this is kind of up to you. You could make it 2x equals 16,000 over x squared. I know x can't be 0 already. Then we could multiply by x squared, so 2x cubed equals 16,000.
Yeah, it seems like
Divide by 2 and x cubed is 8,000. Okay? So what is that? What does x equal then? What's the cube root of 1,000?
8,000?
What's the cube root of 1,000? 10. What's the cube root of 8? 2.
Two.
So it would be 20. Yeah,
Or x 10. Must be on the map.
that's all right. Okay, you can use your calculator. It's okay. All right, so x is 20. Now, is that a minimum? Well, since we don't have endpoints to compare it to, okay, we don't have endpoints, and we know that x has to be greater than 0, so we don't have any points where the derivative is undefined, and we don't have endpoints, so really the only point that the only possibility, it looks like, is at the critical point. So let's just prove that that's a minimum. Okay? So if I use a sign diagram real quick, 20 with my derivative, if I were to plug in 1 into my derivative, I'd get 2 times 1 minus 16,000 over 1. That's definitely negative. So it's decreasing. That's a good sign. If I use something bigger than 20, let's say I use 100, I'd have 200 minus 16,000 over 100 squared. So that would be 10,000. Okay? So I have 16 over 10. 200 minus 16 tenths is positive. Okay? So I just proved that there is a min at x equals 20. Okay?
So if you were testing the endpoints, you know, critical values is the exact same thing, but with the endpoints, you could just put the endpoints on the sign diagram and then test them below. It works the same.
Well, if we had endpoints, and really this is kind of what you can do here. We'll see this with another one here, but if we had endpoints, we could actually just make a little table of values. So here's the left side, here's a critical value, here's a critical value, and here's the right side. And you could just plug them into your function, and whatever the highest one is your max, whatever the lowest one is your min. Okay?
Where did you get 200? I'm confused for.
Where did I get 200?
Yeah.
Oh, I was, oh wait, sorry, that would have been actually 2,000, because we were trying
Oh,
100. We were trying it for when x is 100, so, oh no, it was 200, because it's 2x. 2 times 100.
oh.
All right, so our final answer, what were we asked to give?
Where the surface area found the most economical shape.
Okay, so if you're gonna describe the shape of this thing, you would need to give not just X, but H as well, okay? To really describe the shape, you would want to tell, okay, the base is this by this, and the height is this, okay? So, you should make the container, all right, 20 centimeters, have a 20 centimeter square base, and a height of, well, it's 4,000 divided by x squared. Well, x squared, 20 squared is 400. 4,000 divided by 400 is 10. Okay? So we need to make this to have the minimum surface area and still hold 4 liters. We need to make it 20 centimeters by 20 centimeters and 10 centimeters tall. Okay? And now we've actually answered the question. So I know that's a long kind of process here. We took our time through it, all right? But as you get the hang of it, you know, it'll speed up. Sometimes the most challenging part of this is actually, you know, figuring this out. What function am I actually supposed to use? Once you get there, it's actually relatively simple, okay? But figuring out what function you're supposed to use, and then maybe also with finding the domain that's reasonable, okay? You know, that's where you're going to do a lot of the work for the problem, okay? Let's try another one here, okay? Here we have a manufacturer making X number of items per day. Now we talked earlier about cost as the marginal cost being the derivative of the cost function, okay? Here we're going to look at something a little different. It says the manufacturer makes X items per day. The cost function, and that's his total cost, is C of X equals 720 plus 4X plus 0.02X squared, dollars. And the price function, P of X equals 15 minus 0.002X dollars per item, okay? Now notice that's dollars per item. That's how much they are charging for the item, okay? Now it says find the production level that will maximize profits, okay? Well, this is one where you're not really going to draw a picture for it, okay? So we can skip that part. But let's think through how we find profits. We want to maximize profits, okay? How do we calculate profit? Okay, sales minus costs, or revenue minus costs, okay? So your profit is total sales minus total costs, okay? Now, what are our total sales going to be?
Sales is going to be the number of items you sell times.
Okay, the number of items we sell times how much we're selling them for. Well, how much we're selling them for we were given right here at P of X, okay? And if I'm selling all of them, we're going to assume we sell everything that we make here, All right, so it would be x times that 15 minus 0.002x. That's our total sales. Okay? Then we subtract the costs, the cost function that we have up there. So minus 720 plus 4x plus 0.02x squared. Okay? And notice now we have our profits, capital P I'll use, as a function of x. Okay? Does that make sense? Okay. So sales or revenue is the number of items times the price per item. The cost is what we were given. Now, of course, we would want to simplify this, okay? So P of X, we're going to have a minus 720 at the end. That's the only constant term. The X terms, we're going to have a 15X minus a 4X, so that's going to be plus 11X. And minus 0.002 minus 0.02 is going to be a minus 0.022 x squared. Okay? Now, last thing here, what is the domain in this case? What?
Greater than 2.
Okay. X has to be greater than 0. Anything else about X? Logically speaking?
Yes, it's limited by how long you're working, what the machines can do, but we don't know what that is.
Okay, we were not given a maximum production level. You know, if we work 24/7, our maximum production level would be this. That's a real good consideration. We aren't given that information. What else logically thinking through this? We're producing items, right? Can you sell half of an item? No. So X would need to be an integer. Okay, X would need to be an integer. And actually, by the way, you might see this written as X is an element of Z positive. That's positive integers. Okay? Okay. Now, just thinking about this function, before we even do the derivative, what kind of function is this? Negative 0.022x squared plus 11x minus 720. What is this? It's a quadratic. It's a parabola, right? Is it opening up or down? Down, okay? So the vertex is going to give us the maximum. Okay, now if you were given this problem and just told to solve it and you wanted to just find the vertex with methods that you had learned back in algebra or whatever, that's fine. Go for it. Okay, here though we'll go ahead and use the first derivative. It's actually not much harder. If not, it's actually a little easier. What is our derivative here?
Negative 0.00, or no, just 0.044
Good.
plus 11.
Plus 11. Okay. Okay, so now we need our critical values. Okay. So I'll subtract 11. Divide by a negative 0.044. And what do we get there? 11 divided by 0.044.
250.
What is it?
I got 250.
250?
Yeah.
Anyone else get that? All right, good. All right, so 250. Now that's nice. That's already an integer. Okay. So now we test the endpoints. Well, the endpoints are 0 or whatever else would make the profit equal 0, both of which we know are going to be lower, okay? These are x-intercepts of P, which are lower, okay? So we don't even need to bother with those. This is where you could save yourself some work. Is there anywhere where the derivative is not defined?
No.
Nope. So we don't need to worry about that. So at this point, we just need to check our critical value. And actually, since we know this is a parabola opening downward, we already know that 250 is the max, okay? So x equals 250 is the, or I should say, is where the vertex is. Now this isn't something you necessarily have to write down, but that's what can be going through your head. Okay? So the answer is they should produce they should make 250 items a day.
It sounds so simple in terms of production.
Well, we don't know what they are. Maybe it's cars or something, or okay. Now, does it ask us for the maximum profit? No. It just says find the production level. Could we give the maximum profit? Sure, if we wanted to, but we don't have to, because that's not what the question was asking for. Okay? All right. So let's take a little bit of time. I want you to practice with. I've got a couple of these to practice with. All right. So let's take a little bit of time, and then we can look at a few more later.